Good day, students. Welcome to another online session for the course Digital Logic Design. My name is Ali Roman, and this session is specifically designed for the students of Software Engineering 3C students. In this session, we will be focusing on the De Morgan's theorem, and we will see the implementation of De Morgan's theorem. And we will continue our previous discussion, which we have stopped while discussing the basic primary gates. So first of all, let us see the contents which we will be covering in today's session. So we will be having the introduction and the review of the previous class, what we have studied in the previous class. Then we will switch to the De Morgan's theorem and its implementation with examples. And we will see the two versions of the theorem. One is for based on the multiplication, the Boolean multiplication of the AND operation, and one is based on the or the Boolean addition operation. Then we will see how this De Morgan theorem will help us simplifying the things and converting the Boolean function that has been represented in one form to another form. Then afterwards we will be discussing the multiple input gates, how to represent multiple input gates, and at the end we will see the logical gates ICs and that are being used in order to verify your concepts in your lab portion, which you are using multisim software. So to start with, in our previous session, we will have discussed about the basic primary gates, and we have discussed that AND, OR, and NOT gates are basic primary gates basically, and AND basically performs the Boolean multiplication, and OR basically performs the Boolean addition. And then we have seen and represented that in terms of truth table, in terms of Boolean function, and as well as in terms of the logical diagrams. We have also discussed their implementation. Then we have also discussed the NAND and NOR gates that are known to be the universal gates. And those are the gates that are used in order to implement any gates. That's why that are these two specific gates are called the universal gates. So students, to start our discussion, as far as the reference seedings and acknowledgements are concerned, we are at chapter number 1 of the book Digital Design with Introduction to Verilog HTL, and also we are starting chapter number 2 that basically covers the Boolean algebra, and as well as this De Morgan theorem is well illustrated in chapter number 2. As far as the slides are concerned, the slides are basically originated from the textbook, and as well as these slides are mainly edited by Sir Khalid Ibrahim. So we are grateful for them to provide the template. Now to start our discussion, till now we have discussed the basic implementation and the symbolic representations for the basic primary gates and the universal gates, NOT and NOR gates, and specifically the NAND and NOR gates were discussed in the previous session. So in today's session we will be focusing on De Morgan's theorem, then the two variants of the gates, for example the exclusive OR gate that is being represented by XOR and exclusive NOR gate, we will discuss their implementation, and afterwards we'll switch to the multiple input gates, and then we'll have a brief introduction about the ICs, the packaging, the stuff that basically used to implement those or carry out those designs of those primary as well as universal as well as the other gates. Right. So to start our discussion, first of all, let us see or revise the concept of NAND and NOR gate, and we'll see the equivalent representation of NAND and equivalent representation of NOR, and we will gonna verify that by means of the truth table. So in this particular diagram, this is the symbolic representation of the NAND gate that consists of two inputs X and Y, and Z is the output. So basically Z is a function of X and Y. We can represent that as Z equals, that is the function of X and Y, and that is equal to X dot operator Y and whole prime. So we will using this notation in our future discussion. This represents the complement or NOT operation. This is the complement, while this represents AND operation. Dot basically represents AND operation, which we have discussed in the previous session as well, and this represents OR operation in Boolean algebra. So Z is the output, that is equals to X and Y whole prime. So this is also the equivalent representation of the Boolean function. So basically this is equal to X dot Y whole prime. So as far as the truth table is concerned, if you see that X and Y, the combination of X and Y, so we have got two inputs, so the maximum number of combinations that can be represented in the truth table is equivalent to 2 raised to power n, where n are the number of inputs. N is equal to number of inputs. So if you got two inputs, how many combinations we have in a truth table? That is 2 raised to power 2 equals 4. If you've got four inputs, how many combinations or how many patterns we have in a truth table? That is 2 raised to power 4 equals 16 possible combination. If we have 8 inputs in a system, then how many combinations we have in the truth table? That is 2 raised to power 8 equals 256, and so on and so forth. So more the number of inputs, more the number of values in the truth table, and truth table got expanded, and definitely if we've got more number of inputs to trace out all the possible combinations in the truth table, that would be take some time basically. So here X and Y, basically first of all NAND gate is basically equal to and then inversion. So this truth table basically represents this stuff. So we got an AND gate that has input X and input Y. Then the output of AND gate is called W, that is been inverted to produce C. So basically this truth table represents that combination. So W is equal to here in this case W equals to X dot Y and Z equals to X dot Y prime. Similarly, if you see the other representation, basically these two representations are equivalent. That representation is called negative OR basically. So negative OR is basically equals to the NAND operation basically. So if we and these bubbles basically represents the NOT operation. So if we invert our inputs and then construct the OR operation, then the result that is being produced by this gate is equal to the result that is produced by the NAND gate, and we can see and we can verify from this truth table. As far as the expression is concerned, we can represent it as Z equals X prime or Y prime. So we can clearly say that, or we can claim that X dot Y whole prime equals to x prime or y prime. So this is basically the De Morgan theorem that has been applied on this dot operator. So let us first see the observations which we can see from this expression, that if we apply the De Morgan theorem, or we can say that if we invert a Boolean function in such a way that, for example, x and y is a Boolean function of the AND gate that is been inverted. So what we can observe that this dot operator, let me use some other ink, this dot operator is being converted to this operator. So first observation is, if we invert any complement, that dot is being converted to plus and vice versa. Secondly, the inputs are inverted. See, here we are applying x and here we are getting x prime. Here we are applying y and we are getting y prime. So inputs are inverted. So the first version of the De Morgan theorem states that if we invert a function that is of two literals, x dot y prime, so that equals to x prime or y prime. So what we do is we invert all our variables and then we convert, if there is a plus operator, that has been converted into dot operator, or operator has been converted to the AND operation, and AND operation is converted into OR operation. Okay, so this is the first version of the De Morgan's theorem. So if we have to apply this on, for example, we have got a function of two literals x, and we are constructing the OR operation between those two literals, and we are inverting, then just remember the principle. This plus operator is first converted to the dot operation. Secondly, we have to invert the input. So x is being inverted to x prime and y is being inverted to y prime. So this is the second version of, or the second theorem of De Morgan. So here we can see that this NOR gate is basically equals to the negative AND. This is called the negative AND. These both are equivalent. Similarly, the NAND was equivalent to negative OR, and this is basically the De Morgan theorem that states that. See, this is the version. So the alternative form in your book that has been used in order to represent this theorem is x or y whole prime equals to x prime and operation, that is represented by dot y prime. So same principle that has been applied, which we have used for the first version, that has also been used for the second version also. So this is the symbolic representation of the graphical representation of theorems, which you can state that here the NOT operation is being specified by bar operation. So if you are confusing with that, we can represent it as A dot B bar, that is equivalent to, or that is equal to A bar or B bar. And similarly this thing, A or b whole prime. So basically, these are the equivalent representations to represent the not operation. In your book, this representation is used in order to invert. So we are sticking with that representation. But if you are comfortable using this representation, it's okay. So that is equal to a bar dot b bar. Okay, so I hope so. Now the concept of De Morgan's theorem is very much clear. Basically, that deals with the inversion of the function and how the terms in a function that are being converted into their equivalent representation, uh, which we have proven by use of the theorem. And we have seen both versions of the theorem. One was with respect to the dot operator, and one was with respect to the plus operator, the Boolean operators. So these are the truth table representations, and we can see that if we construct the truth table of the left hand side and then we can construct the truth table of the right hand side, and we can see that both are equivalent. So this is the first version on a dot operator, both are equivalent, and this is the second version on a plus operator, both are same basically. Okay, so let's continue with that. What we have studied, we first of all we invert all the variables. Let us conclude the De Morgan theorem. Then we convert the symbolic representation, the operations that have been applied in that particular function, as and is been converted to or and or is been converted to and if required the result is being complemented. For example, for the left hand side, if we complement the result, that is equivalent to the equivalent form constructed and generating the result, both should be the same. Now let us see the examples here. I'm going through the first example basically, so you can carry out with the rest of the examples. The first example states that we have an input x. We can represent it as x prime or y prime, and if we are generating its complement, then what would be the result? We are computing this thing. So remember the concept of the De Morgan theorem. Now your input is already in a complemented form, and we are taking its complement of the whole function. So what De Morgan theorem states that invert your inputs first of all. So x complement is your input that is being inverted. So x complement was the input that is being inverted. Then y complement was the input, or y prime. We can also call it as a y prime. Y prime was the input that was inverted, and this plus operation basically is being converted to the dot operation, and here we go and get the result that is equivalent to x dot y. Okay, which you can prove from this expression as well. For example, we've got a variable x, we've got a variable y, then we are generating x prime, we are generating y prime, then we are generating x prime or y prime, and then the next thing is we will generate x dot y, and the last term will be x dot y prime. So the combinations of x and y are 0 0, 0 1, 1 0, and 1 1. And now the x prime will be 1 1 0 0, y prime will be 1 0 1 0, and x prime or y prime will be 1 1 1 0, and x into y. Basically now we are focusing on these two combinations, that is basically the AND operation, that is equal to 0 0 0 1, and if we invert that output to generate that, that is equivalent to 1 1 1 0. Basically this thing is equal to this thing. So we have solved the system, and we have proven that the left hand side, that is being equal to this representation. Okay, so you can also verify the remaining combinations. Well, that was all for the De Morgan's theorem. Now let us focus on the exclusive OR gate and exclusive NOR gate basically. So we can implement that gate with the use of AND and OR gates, and also you have seen the implementation as well as in your labs, but we will discuss how we extract those terms in order to generate Boolean function when we're going to discuss the min terms and max terms and the canonical and standard forms of expression in our next class. So right now just we are just representing the basic operation of exclusive OR gate and exclusive NOR gate. So let's start. Let's see how these gates are represented and what are the functionality of these gates. Well, this is the symbolic representation for exclusive OR gate. So the main function which you can see or which you can verify from the exclusive OR gate is that if the inputs are same, if we apply the inputs that are same, the output is 0 in that particular combination, and if inputs are different from each other, then the output is 1. Basically that operation is known to be the modulo 2 addition or modulo 2 operation, which we will see in detail. What do we mean by the modulo 2 addition or operation? So this is the symbolic representation for the exclusive OR. Here x and y are the input and the z is the output. So exclusive OR where z is a function of x and y, this is the representation in Verilog, is a hardware descriptive language. So if you're confusing with that, just ignore that. So in your textbook, the exclusive OR operation can either be represented by this representation, or we can represent z, that is a function of x and y, and that is been represented as x is the input, this OR operation, and we'll circle this OR operation y. So we will use this representation to represent exclusive OR operation in your textbook, which is basically this thing is equals to x prime into y prime. Sorry, we'll use y in its original format, x into y, x prime into y, or x into y prime. We will see how these terms are being extracted from the truth table from the next class, when we will discuss the canonical and standard forms of expression and how these terms are being generated by use of this truth table. Okay, so this is the exclusive OR operation, and this is the symbolic representation. You can either use this representation, or you can also use this representation as well. Let me draw that. Both are same basically. There is no difference between both the representations. Let me use some other ink, color. Um, for example, we can also draw this. Not so much difference. Both are same symbol, except here we are not interconnecting these two lines. Here the lines are also connected, so both are same basically. So X and Y, and I'm getting Z here. Well, okay, that was the exclusive OR gate. These are the representations in different platforms here. uh, we will be using this representation which I've discussed with you earlier. And now discuss the another version of the gate, that is exclusive NOR gate. So if we invert the output of XOR gate, we will generate the output for the exclusive NOR gate. So exclusive NOR gate is basically, we can represent that in such a way that basically we are inverting our output of the exclusive OR gate. So here we've got X, here we've got Y, and if we invert by using NOT gate, this is Z. So this NOT gate is being represented by this bubble here. So if you can see that if the inputs are same, the output is 1. Basically we are generating the complement of this exclusive OR, and if the inputs are different basically from each other, the output is 0. Okay, so that is the exclusive NOR gate. These are some representation of the exclusive NOR gate in different platforms. We will be using X exclusive OR with Y. For example, X and Y are the literals. This representation to represent the exclusive NOR operation, and that is mathematically equals to X prime into Y prime plus X into Y. So we can also represent in that particular notation, and these are the truth table to represent the operation of the exclusive NOR gate. So basic application for the exclusive NOR gate is the equality detector to check the inputs are equal or not. So if you found that the inputs are equal, that gate identifies 1, and if the inputs are complement to each other, the output is 0. We can when we will implement the comparator circuits in the combination logic design, then we will be using this property frequently in order to represent the equality operation. So let us summarize what we have studied till now. We have studied about the different gates and the behavior of the different gates with application of the input. So this is basically a two literal system, the two input system, where A and B are the inputs, and the outputs of the respected gates are shown in the table. For example, the AND operation, if you construct the NAND operation, or NOR, exclusive OR, and exclusive NOR operation. Now coming to the multiple input gates. For example, if we have a system of the literals that are more than 2, how we're going to represent that? So basically we can represent by the standard notation. For example, this is an AND gate with 4 inputs, and this is the NAND gate with 1, 2, 3, 4, 5, 6, 7, 8 inputs. And similarly, we can also represent in this notation. For example, if you've got OR gate with 1, 2, 3, 4, 5, 6, 7, 8 inputs, and the NOR gate with 1, 2, 3, 4, 5 inputs, so we can see that the multiple inputs in that particular setup. Okay, so we can use both representations as far as with our convenience is concerned. So these are the multiple level inputs, so multiple input gates basically. We can also represent this gate, for example, in this format. Both are equivalent. If we restrict that, we have to implement this four literal system by using the gates that only consist of two inputs. So we can also represent that. For example, this is A. The first input A is A, then B, then C, then D, and we have to implement this operation by using the two input gates only. Then we can represent it as, first of all, we've constructed the AND operation between A and B. Then we have constructed the AND operation with C with the result of A dot B. This is A dot B basically. And then we are using another AND gate. So this is basically Z1. And this term is A dot B dot C. Okay, so if you see the economical approach here, and let us assume that one gate or one IC, let us assume that one IC contains one specific gate, just for the example. Otherwise we know that the standard ICs can contain the four gates of the two input gates, uh, and as well as you will learn that how many multiple input gates can be carried over in a single package when we'll discuss the IC packaging here. So if let us assume that one gate costs 5 rupees here, and then you can see that to implement that by using two level gates, we have to have minimum 15 rupees, just for the sake of example. And here we can implement that with 5 rupees only, because we are using one multiple input gate that is performing the same operation that has been carried out with this diagram. So the multiple input AND gate works in the same way as the two input AND gates. There is no change in the basic operation, because the AND operation holds the associativity property, and operation holds the commutative property, and also the distributive property. So uh, there is a no change in the output basically. So, and output Z1 is 1. 1 is represented by the high state basically if all the inputs are high. Similarly, with the OR gate, we can say that if all the inputs are low, then in only that particular case, Z2 will be low. And similarly for the Z3, because we are using the NAND operation here, so Z3 is low only if all the inputs are high. Similar is the case with the multiple input NOR gate. So this comes with our last topic of our discussion for the class, that is the logical gate ICs. And here you can see that this is the 14 pin. This representation is a 14 pin dual inline package, that is called to be the DIP package. Dual inline pin package basically. That means that half of the pins are on one side and half of the pins are on other side. So basically these pins are opposite to each other in the representation. So these are the dual inline packages. These are the inline pins, and both sides contain equal amount of pins here. This is a 14 pin package. You can see that the number of pins are 14. So how to identify the first pin? You can see that this cut symbol and this dot symbol basically represent the position of the first pin, and we start our counting counterclockwise in order to identify the pins. So 1, 2, 3, 4, 5, 6, 7, 8, and then in this direction. First pin and the last pin are opposite to each other, which you can see from this representation also. The pin number 14 normally represents the VCC or the voltages that have been applied to operate this particular IC, and pin number 7 is known to be the ground potential. We have to connect that with ground, and These specific set of ICs that consist of these gates have the same pin orientation, but depending upon the IC number, that specifies the operation that is being implemented and in that particular IC. There is a change in pin. For example, the NOR gate to input NOR gate, which you can see the pin orientation is bit changed as compared to the other one. So this is the only difference which you have to take care if you are using 7402. This is the internal structure for 7400. This is the quad NAND gate. Quad means we have got 4 NAND gates in that particular IC, and this is the symbolic representation and pin connections. If you want to use the NAND gates, and you can use these 4 NAND gates in one single package, that is 7400. So these are some more ICs. For example, 3 input gate ICs with the pin orientation that is been specified here, and these are the ICs that has the 4 inputs and their pin orientation is specified here. How we're gonna get this pin orientation and all the data? Because if any manufacturing company is manufacturing some particular IC, they're going to provide you a specification document that is known to be the data sheet. Basically, that tells us all the information regarding that particular IC, how to use that, what are the constraints, what are the specifications. All the things are mentioned in the data sheet basically. So if you are given some particular IC to work, and you don't know how to interconnect your connections with that particular IC, the first thing which you will do is to download the data sheet and then verify the connections from that data sheet and then use that particular component in your digital design. And similarly, there are some more ICs here. So, well, that was all for today's discussion. In today's discussion, we've discussed about the basic theme of the lecture was focusing on De Morgan's theorem, and then we've discussed about the exclusive OR and NOR operation, and afterwards we've switched to the multiple input gates, and at last we've discussed the packaging and the ICs that are used to implement those and their pin orientation, which if your labs were in physical orientation, you will be using that particular ICs in order to implement your digital design. But I hope so in the QtSpim you are also using the same ICs. So till now, I hope so everything is cleared. In the next session, we will be focusing on canonical and standard forms of expression or in order to represent the Boolean function. Till now, take care. Have a good day.